In this video, we're going to talk about reaction mechanisms. I had mentioned at the beginning of this chapter that kinetics looks at the rate of our reactions, but also the sequence of steps that get us from reactants to products, and that is our reaction mechanism. So reaction mechanism, and we're going to look at it pretty simplistically. If you go on and take organic, you'll spend a lot of time looking at reaction mechanisms in much more depth than what we're going to look at here. But it's the sequence of steps that describe the pathway from reactants to products. So many reactions, when you're given our net chemical equation, that's literally the net. Many reactions don't just take place in one step. You're going to form intermediates, and it's going to take place in more than one step. And I will give us some examples of that in a minute. Some terminology first. Each individual step, so if a reaction takes place in 3 steps, each of those 3 steps is called an elementary step. So an elementary step. These are the individual steps in the mechanism, or the individual reactions in the mechanism. Our elementary steps, we add them together to give us our overall or our net reaction. And that's what we're used to seeing is our net equation. Equation is actually the better word to use here. So the individual steps are called elementary steps. Our overall equation, you could use the word overall if you wanted, or you could use the word net equation. Elementary steps are generally described in terms of their molecularity. So what that really tells us is how many reactant molecules are producing, or are involved, I should say, in that elementary step. So elementary steps can be described in terms of their molecularity, kind of a weird word. So if something was considered a bimolecular reaction, it means there's 2 reactant molecules. If something was unimolecular, it means there's 1 reactant molecule. So unimolecular, bimolecular. If we had 3, we would actually say termolecular. So here, 1 reactant molecule, 2 reactant molecules. They could be the same, so you could have 1 reactant with a coefficient of 2 in front of it that would be considered bimolecular. Termolecular, 3 reactant molecules. Right? I'm not saying 1 reactant, I'm saying 1 reactant molecule in my balanced equation for that elementary step. A couple of quick examples for those. If I was to write O3, so that's ozone, going to oxygen plus just a single oxygen atom, this would be considered a unimolecular reaction. Right? I have 1 reactant molecule. It has a coefficient of 1 in front of it. If I was to look at NO2, so nitrogen dioxide, plus carbon monoxide, going to nitrogen monoxide plus carbon dioxide, this would be considered a bimolecular reaction. I have two reactant molecules, so bimolecular. We could also have a bimolecular reaction by having two in front of a coefficient of 2 in front of one reactant. So 2HI makes more sense to just show you, going to H2 plus I2. So again, I have two reactant molecules, right? There's two HIs, so HI plus HI. This would also be considered bimolecular. An example of something that's termolecular, we could have two nitrogen monoxides plus chlorine going to two NOCLs. And here I have three reactant molecules, right? I have two nitrogen monoxides plus chlorine, so three molecules total, so termolecular. Write the rate laws for elementary reactions based on its molecularity. And this only works for elementary steps. We cannot do this for the overall reaction. So for elementary steps, and again, it's really important that it's only for elementary steps. So I'm going to underline this in red because we cannot do this for our overall reaction. The rate law can be written based on its molecularity. Meaning I can just look at my balanced equation for each elementary step and write the rate law from that. Remember, our rate laws for our overall reaction, we can't do that, right? We could only get that experimentally. If I have my elementary steps, though, I can write a rate law for each of those individual steps. Right? Remember, my rate laws tell me how fast it is. So each step has its own rate, right? The first step, second step, third step, I would have a rate law for all of those, plus I would have an overall rate law. So for elementary steps, the rate can be written based on its molecularity. Can not necessarily, I am going to have one exception. Let's say always. Let's just say not. Cannot do this for the overall reaction. And again, there's one exception, however, which we will get to. But in general, you cannot just look at it and write the rate law. For elementary steps, we can though. So for elementary steps, I can do that. So using my examples from above here, remember a rate law is always the word rate, an equal sign, a lowercase k, and then for elementary steps, I'm just going to take my reactant, right? Rate laws are always written in terms of reactants, not products, and I am going to raise it to a power equal to its coefficient. So since I have a coefficient of 1 in front of ozone, I'm going to raise that to the first power. My rate law for this one, K, I have both NO2 and carbon dioxide. I have 1 mole of each, so each get raised to the first power. This one, rate, lowercase k, I have HI, and I'm going to raise that to the second power because we have a coefficient of 2. If I look at this last one here, I'm just going to run out of room if I put it right next to it. K, nitrogen monoxide, I'm going to raise it to the second power again because I have that coefficient of 2 multiplied by my concentration of chlorine. So those would be the rate laws for those elementary steps. My first one here is a first order reaction, right? Both of the bimolecular ones, these are both second order. And this last one is a third order reaction, right? We got the order by looking at the exponents that we're raising our concentration of reactants to. So unimolecular, first order, bimolecular, second order, termolecular is going to be third order. The rate determining step. abbreviated RDS, is the slowest step of our reaction, the slowest step of the mechanism. So whichever elementary step is the slowest is my rate determining step. It's called rate determining because it determines the overall rate of our reaction, right? Our reaction can never proceed faster than its slowest step. So my rate determining step, this is the slowest step of the mechanism, right? It's our slowest elementary step. And it determines the overall rate of the reaction. Right? Our reaction can never proceed faster than its slowest step. So, rate determining step. Other terms before we get into an entire mechanism: intermediates, an intermediate is going to be a molecule or an atom. It's going to be a species that we actually produce in one step and then consume in a subsequent step. So it's going to be a product first and then a reactant. So produced in one step and then consumed in a subsequent step, so later on. Because it's a product and then a reactant, it does get canceled out, so it's not part of our net equation. So when we write our net, it is something that gets canceled. Again, be really careful, because I'm going to give you another definition here that's going to be slightly different, but this is going to be produced first and then consumed. Another way to say it, it's going to be first, it's a product, then a reactant. We can also have catalysts. And we'll talk more about catalysts in a little bit, but these are also something that's not going to be part of my net equation. They are going to get canceled out when we add together our elementary steps. But this one's going to be the opposite. Catalysts are going to be something that we put into the reaction and then get back out of the reaction. So we're going to add it. It actually speeds up our reaction. Is one of the ways that we can increase our reaction rate. But then we get it back out. It's not consumed. So this is added to the reaction, but is not consumed by the reaction. And it functions, and again, we will talk in more detail about it in a little bit, to increase reaction rate. Because we're putting it in and getting it back out, it does cancel, so it's not part of the net equation or overall equation. This one, just be careful, it's the opposite. It's going to be a reactant first because we're adding it, and then a product second because we're getting it back. So first a reactant, then a product. So put it in, get it back out. Intermediates, we produce and then consume. Both of them get canceled out. Both of them are not part of our net equation. Let's do an actual example here. So given two steps, I have S2O8 with a -2 charge. I'm reacting it with iodide ions, so I-. We're producing 2 sulfate ions. Sulfate is one of those polyatomic ions you're expected to memorize in 151. And then iodide with a positive charge. I know that looks kind of weird. And then I plus I minus going to I2. So these are our 2 steps. My first step is my slow step, and my second step is faster. So 2 elementary steps. And we're going to do a couple things. So our questions is we're going to write the overall reaction. We're going to identify any intermediates and or catalysts. We're going to determine the molecularity of each step and write its rate law. And one more, we're going to determine which step is rate determining. And then I am going to add part 5, but we're going to do this first. So adding these guys together, we are going to treat it just as if you were adding 2 equations in algebra. So these arrows, think of those as kind of your equal sign. Everything that's the same on the reactant side is going to get added together. Everything that's the same on the product side is going to get added together. And then anything that's on the reactant side and the product side is going to get canceled out. You would have added reactions when you were doing Hess's law in 151. So this is a very similar, it's the same concept really. So looking at it, what can we cancel? So I have iodide here, sorry, I plus here, and I have it here. So those go away because they get canceled out. And then those are the only things I have in common on the reactant and the product side. I'm going to add my reactions then, after we're sure that everything can be canceled. I have S2O8 2-. I have 2 iodide ions, right? These guys get added together. That's going to 2 sulfate plus I2. So that would be my net equation. So that's my answer there. Any intermediates and or catalysts? Remember, intermediates are things that we're going to produce in one step and then consume in a second step. So it's a product first and then a reactant. Catalysts are something that we're going to put into it and then get back out of it. So it's going to be a reactant first and then a product. So what do you guys see here? The only thing I canceled is I plus. That's the only one that's, up for debate here. And what is it? It's an intermediate catalyst. Good, it's an intermediate. So I plus is an intermediate, right? We made it and then we used it up. And there's no catalysts in this reaction. So no catalysts. Determine the molecularity of each step. So I have one reactant molecule and another reactant molecule, so that's bimolecular. When I write the rate law for it, we'll squish it down here somewhere. It's going to be S2O8 2- multiplied by the concentration of I-. This is for my first step. And then for my second step, which is also bimolecular, right, I have I plus and I minus. These are going to be both second order, right? They have coefficients of 1. Rate law for my second step. Which step is my rate determining step? My rate determining step is going to be the slowest step of my reaction, and that's my first step. So slowest step is going to be step number 1. Guess I should have numbered these here. So the first step. The second part that I want to add, or the fifth part really, sorry, is that we had said that you cannot determine the overall rate of the reaction from looking at that reaction, right? We could do that for elementary steps. I'm going back up here to this part, right? For elementary steps, the rate can be written based on its molecularity. We cannot do that for the overall reaction. There is one kind of exception. We're still not doing it from the overall reaction, but what we can do is we can look at the elementary steps. If, and I will write this down, if your rate determining step is the first step, then the overall rate law is the same as the rate law for that step. If it's not the first step, then it's more complicated, but if it's the first step, then our overall rate law is that rate determining step. So let's write that down. If, and it's a big if, the first step of the mechanism is the rate determining step, then the overall rate law is the same as the rate law for that step. So the part that I want to add is, what is my overall rate law? And my overall rate law, right, because my first step is my rate determining step, right? Determine the rate determining step number 4 here, it's the first step. Because the first step is the rate determining step, my overall rate law is the same as the rate law for that step. So my overall rate law for this reaction is the rate law that we wrote for that first step. And again, this only works if the first step is rate determining. If the second step is rate determining, then it's a more complicated process. Sometimes it's true, sometimes it's not. We're just going to say that we can't determine it. But if the first step, right, if the first step is the rate determining step, then the overall rate law is the same as the rate law for that rate determining step. Another example. This one is going to have 3 steps. So step 1, step 2, and step 3. My first one, 2 nitrogen monoxides going to N2O2, and then N2O2 dinitrogen dioxide plus hydrogen going to dinitrogen monoxide plus water. And then step 3, dinitrogen monoxide plus water going to nitrogen plus water. So we're going to determine the overall reaction, the molecularity, we're going to write the rate law each step, identify any intermediates and a catalyst, and then also if, and I'm going to move this down a little bit because I want to write my answer for my net right after my elementary steps. So if the overall rate law is K times the concentration of NO raised to the second power times the concentration of hydrogen, can we determine which step is the rate determining step? Okay. I know I didn't write down all the instructions, but they're essentially the instructions from before. So we're going to write the net, we're going to identify intermediates, catalysts, we're going to write the rate law for each of those steps. And then if our overall rate law is this, which step is rate determining? So I'm not going to put slow and fast on there. We're going to see if we can figure that out. So my net equation first. Again, we're going to add these together, reactant sum together, product sum together. Anything that's on the reactant and the product side gets canceled out. So this would be a great time for you to hit pause, answer this yourself, and then when you're ready to check your work, hit play again. Okay, hopefully you guys worked on it. So dinitrogen dioxide gets canceled. I am going to cancel an N2O, so dinitrogen oxide. And then I am going to cancel one of my water, right? I do have 2 water here and 1 water here, so one of those is going to get canceled. And then I'm going to write what we got. So I have 2 nitrogen monoxides left. I have hydrogen going to nitrogen plus water. So that would be my net reaction. My rate law for this first step, because I have 2 nitrogen monoxides, I do raise that to the second power. So this is a bimolecular reaction, right? It's second order. For my second one, N2O2 raised to the first power multiplied by the concentration of hydrogen raised to the first power, also bimolecular, second order. My third step, N2O, water, also bimolecular, second order. So all 3 of my elementary steps are bimolecular. Intermediates, what did you guys get? So there's a couple, right? I'm producing dinitrogen dioxide and then I'm using it up, so that one counts. I am producing dinitrogen monoxide and then using it up, so that's also an intermediate. And then one of my water molecules is also serving as an intermediate, right? We produced and then we consumed, so water. I do have a water molecule as a product, but one of those water molecules is serving as an intermediate. And then I don't have any catalysts again. So none. So our question then, if this is my overall rate law, can I tell which is the slowest, right? Which step is rate determining? I know that if my first step was rate determining, then this would be my rate law, right? If the first step is rate determining, then the rate for the overall reaction, or the rate law for the overall reaction, is the same as the rate law for that first rate determining step. And those are not the same, right? The 2 rate laws that I highlighted in yellow are different. And I had said if it's not the first step, then we can't really tell, right? It's more complicated. So essentially, no, we can't tell. We can tell that it's not the first step. That's all I have. I don't know if it's the second or the third. Another reaction for us, or example, I should say. I'm going to have hydrogen peroxide, so H2O2, reacting with iodide ion, so I minus, going to a water molecule plus IO minus, which is hypoiodite, right? One of the polyatomic ions you would have learned rules for to name in 150 or 151. My second step is going to be another hydrogen peroxide reacting with hypoiodite, going to another water molecule plus oxygen plus iodide ions. And we're going to write the net equation, or overall, same thing. And then if the overall rate law is rate equal to K multiplied by the concentration of hydrogen peroxide multiplied by the concentration of iodide, which step is the rate determining step? So RDS for rate determining step. And then let's also identify any intermediates and identify any catalysts. So write the overall or net equation, right? Two words are the same thing. If the overall rate law is rate equal to K multiplied by the concentration of hydrogen peroxide raised to the first power multiplied by the concentration of iodide ions raised to the first power, which step is the rate determining step? And then what do we have for intermediates and our catalysts? So to write our net equation, remember anything that's the same on the reactant and the product side gets canceled out. Everything on the reactant side gets summed. Everything on the product side gets summed. So I have hypoiodide ions on both sides, so we're going to cancel those. I have iodide ions on both sides, so that also gets canceled. And then when I write everything I have left, I have two hydrogen peroxide, right? One here and one here. So two H2O2s going to two water plus oxygen. So that would be my overall or net equation for this mechanism. Second part, our overall rate law is the rate is equal to K multiplied by the hydrogen peroxide concentration multiplied by the iodide concentration. Knowing that, we want to know which step is rate determining. So remember, we can tell or determine the rate law based on our mechanism if the first step is rate determining, right? If we were to write our rate laws for the individual steps in a mechanism, rate equals K times the concentration of the reactants raised to a power equal to the coefficient. And again, remember that's only for elementary steps. And then we had that one little stipulation that if the first step in the mechanism was the rate determining step, then our overall rate law is the same as the rate law for that first step. And again, that only works for the first step. So our question then, I only have two steps. Is this the rate law for the first step? If it is, then that's the rate determining step. Is this the rate law for the first step? If it's not, then the first step isn't the rate determining step, and it has to be the second because I only have two steps. So if I look, hydrogen peroxide, 1 mole, iodide, 1 mole. So this does match that first step. So our first step is rate determining. Right? That means our first step is the slowest step of our reaction. So the first step would take place slowly, the second step would take place faster than that. Slow and fast, of course, being relative. So again, just want to make sure everyone's on board, right? You cannot determine the overall rate law by just looking at the overall reaction, right? If I was to look at this, I have hydrogen peroxide, right? And I have two of them. If I look at my rate law, let's highlight it here. If I was to look at my rate law, I have one hydrogen peroxide and I have iodide, and there's no iodide here, right? We cannot look at our overall reaction and figure out our rate law from it. The only time you could ever do that is if there's a one-step mechanism, because then that one step is the rate determining step, which happens to not be the case here. I have two steps, right? Clearly given because I'm given two steps. And we do know then if our first step is rate determining, then the overall rate law is the same as the rate law for that first step. If it's not the first step that's rate determining, then we don't necessarily know which one it is. All right, next question, identify any intermediates. Remember, intermediates are going to be species that we make first and then consume. So they're going to be a product and then a reactant. So in this case, IO minus, right? It was a product first, and then it was a reactant in the subsequent step. We produced it and then consumed it. Catalysts are going to be opposite. Catalysts are going to be things we put into it and then get back out of it. So they're going to be a reactant first and then a product, in this case, I minus, right? I'm putting it in, it's on the reactant side, and then I'm getting it out, it's on the product side. So I minus would be a catalyst in this case. I do want to revisit energy diagrams here real quickly. Remember when we were doing energy diagrams the other day, we said that it's a graph of our energy versus our reaction progress. And the ones that we were looking at previously all were single step reactions. So no intermediates, no elementary steps. It just proceeds in one reaction. So my overall reaction is my elementary step, right? We have our reactants, we have our products, we have our transition state, and then we had our activation energy. And that was the energy difference between my reactants and that transition state, right? That was the minimum amount of energy that we have to put into our reaction for it to proceed. If I was to look at two energy diagrams, and I'm actually gonna, let's redraw both of them because I want to make it more exaggerated. So I'm going to draw two more. So I'm going to start here and I'm going to go up and then I'm going to come back down. That's pretty ugly, but we'll go with it. So energy, reaction, and actually I want to try to make it a little bit better. So we're going to start, we're going to go up, and we're going to come back down. So my activation energy again is this difference. And then if I was to draw one right next to it, I'm being lazy on you here. So I'm going to draw one next to it, but I am going to redraw the actual curve here. I'm just keeping the axes. So I want to start out at essentially the same spot, but I'm only going to go up to here, and then I'm going to come back down to essentially the same spot. So I want my reactant energy and my product energy to be the same in both of them. The only difference in these two is going to be my activation energy. Right here, this is my activation energy. And if we keep in mind, right, not all collisions are effective, right? They have to collide with enough energy to be able to get over that energy hill, right? That collision energy needs to be equal to or greater than that activation energy. So let's say our frequency factor is the same. So ignoring kind of orientation and frequency collision, of these two reactions, which one would you guys expect to be faster? A or B? Just kind of thinking about it. Hopefully you're thinking B. If you're not, I'll tell you why it should be B, right? I need less energy, right? My activation energy is smaller, so more of those collisions are going to have enough energy, right? Assuming we're doing this at the same temperature also, more of those collisions are going to be able to get over that energy hill. Right? Let's say you're going to walk to the store and there's a big hill you have to climb over, or if you're going to walk to the store, same distance, but it's just, there's no hill, right? Which one's going to take longer, having to get over that big hill? And this is, you're not walking there, but collisions, right? It has to have enough energy. If it's a lot of energy, then the odds kind of go down, right? Less energy, the faster the reaction, right? More of those collisions are going to lead to products. More of those collisions are going to be effective. So smaller activation energies those are going to be faster reactions. So this is faster. It has a smaller activation energy. So if I was to look at something that proceeds in 2 elementary steps, so I'm going to give us another example here. I'm going to have 2 NO2 going to nitrogen trioxide, right? It's not nitrate because it's not an ion. If it was NO3 minus, it would be nitrate, but it's just nitrogen trioxide. So 2 elementary steps. We can write our net just for fun, right? In my net, I'm going to end up canceling NO3. That's going to be an intermediate, right? I made it and then consumed it. And then I'm going to cancel one of these NO2s. So I'm going to have nitrogen dioxide plus carbon monoxide going to nitrogen monoxide plus carbon dioxide. And my first step is going to be the slowest step. So my first step is my rate determining step. What that means is if I was to look at an energy diagram, my activation energy for the first reaction is going to be bigger than the activation energy for my faster one, right? We had just said faster reactions have smaller activation energies. So if I was to sketch an energy diagram for this one, and I'm going to make my y-axis or my x-axis a little bit bigger. Not only am I going to have 2 bumps, right, because I have 2 steps, but I need to make sure that my first activation energy is larger than my second activation energy. So I'm going to start somewhere here again. I'm going to assume it's exothermic. I'm going to go up. I'm going to dip back down a little bit, and then I'm going to go up again. And I don't have information to know the relative height of my 2 transition states. Like this peak could be higher than this peak or vice versa. But I know that I'm going to go up. I'm going to dip down a little bit. I'm going to go back up, and then I'm going to dip down a little bit. And I shouldn't, my lines are pretty rickety here, but this, you know how it kind of shoots back, it shouldn't, because I'm not losing time and should continue to go forward. It's pretty ugly. I'm just going to draw it again. So up, down, up, and then back down. And it's not a whole lot better, but hopefully you get the idea. So reactants, products, I do have a transition state. And then here is where my intermediate is going to be. And then transition state. And it's not even just the intermediate, but it's the products from the first step. So kind of if I was to look at my reactions here, this is what goes here. This is what goes here. And this, which is why we just normally say intermediate. And then this is going to be my products. Transition states are where we then are breaking and forming those bonds. So I have 2 transition states. That might have been kind of confusing, but I won't ask you to identify those. Just do know that you're going to have 2 transition states and you're going to have that intermediate, meaning you're going to have 2 activation energies. This second activation energy is the energy difference between my intermediate, which is my reactant for that second step, and I'm going to put a subscript 1 and 2 on here and that transition state. And then because my first step was slower, this first activation energy is larger than this second one. If my second step was slower, then I would want to reverse those. I want my second activation energy to be larger than my first one. So faster reactions have smaller activation energies. If it proceeds in more than one step, you're going to have kind of a transition state for all of those, right? If we had something that proceeded in 3 steps, I'm not going to draw the whole thing, but it would go up, come down, go up, come down, go back up. Those are probably not all equal, but you're going to have 3 transition states, 3 activation energies. I won't ask you to draw something like that, but do be able to identify the parts. So kind of going back and looking at this again, reactants, intermediate, product, my 2 transition states, my 2 activation energies, making sure that the slow one, right, has the larger activation energy. I did promise that we would talk a little bit more about catalysts. Right, we said catalysts are something that's put into the reaction and it's also not consumed, so we get it back out. And its purpose is to increase the rate of that reaction. So it increases the reaction rate. That's why we would use a catalyst. We would want to speed it up. And it's not consumed. So increases the reaction rate without being consumed by the reaction, right? We put it in and then we get it back out. And different catalysts function differently, but essentially what they're doing is they're generally lowering that activation energy, right? We said faster reactions have smaller activation energies. So if we want to speed it up, we can lower that activation energy. And they can do that in different ways. How different catalysts work, it depends on the catalyst itself, but that's kind of in general what they're going to do. So they speed up the reaction by providing a set of elementary steps with more favorable kinetics. Usually, and if you've learned about catalysts before, you probably learned that that's how they did it. The word usually was probably missing, but we're going to add that by usually lowering the activation energy. So if I was to look at an energy diagram, and I'm just going to do this with a single reaction or a single reactant. Sorry, single step, like it's not confusing enough. I'm gonna have one bump. So energy, reaction, I'm gonna go up and then come back down. Again, I'm making this one exothermic. If this is my activation energy here, then if I was to add a catalyst to it, right? If I look at my activation energy now with that catalyst, and that line wasn't quite all the way on the top. We want to find the peak. It's kind of messy, but that's now my activation energy. Remember, smaller activation energy, faster reaction. So we lowered that activation energy. And again, how it does it can vary. I can draw another one. And if I wanted to add a catalyst, we could say maybe this one does something like this, right? Either way, it's going to be lower. So it's not always just taking the same pathway and lowering it. My series of steps could be different, but however it's functioning, it is increasing my reaction rate, usually by making that activation energy lower.